Right, welcome to week 4, Graduate Statistics, University of Cincinnati. This is video lecture 2. So we finished the previous video formalizing what mean, median, and mode are and making a distinction between parameters in the population and sample statistics. Now let's check your understanding. Sleeping in college. A recent article in a college newspaper stated that college students get an average of 5.5 hours of sleep each night. A student who was skeptical about this value decided to conduct a survey by randomly sampling 25 students. On average, the sampled students slept 6.25 hours per night. Identify which value represents the sample mean, a sample statistic, and which value represents the claimed population mean, a population parameter. Pause the video and give yourself a few moments to think about this. Now, if you decided that 5.5 is the claimed population mean, you're right. So that's what the newspaper was saying, the population of all college students, that's how long they sleep. But the student conducted a survey and grabbed a sample, a random sample, and found a value that was not quite that, but larger than that. In future classes, we'll discuss the idea of sampling repeatedly from the population and how each sample will have a mean that approaches the population mean, but that is not quite the population mean on target. We'll discuss that and what it means for statistical testing. Don't worry about this now. At the moment, I just want you to be able to differentiate what a population mean is. It would be the mean if I were to assess the sleep patterns of every one of the college students. We tend not to do that, so we tend to try and estimate that population mean from samples, right? And in that particular sample that the student took, the average hours of sleep was 6.25. All right. So now let's think about how to compute these different measures of distribution center. So here are 9 students' exam scores. And if I were to compute the mean, as you all probably know, you sum all of those values and you divide by the number of observations that you have, in this case 9, and that would be your mean. If you were to compute the median, then what you do, you have to put the scores in order from smallest to largest, and then the median will be the middle of the distribution. Looking at these calculations, even though we're not going to do them by hand, helps us see why I mentioned that the mean is influenced by the extreme values, because they count in the addition, and how the median is not. Because even if 95 turned out to be 110, even if it was 1,000, if this one value was 1,000, that would impact the mean tremendously, but the median will still be 87. That's why skewed distributions are better characterized by the median, and symmetric distributions are better characterized by the mean. And the mode here is the most frequent value, and the one that repeats the most is 88. It's actually the only one that repeats more than once. Now, what if there is an even number of scores? What happens with the median? Well, what happens is that we get the 2 middle ones, and then we average them, and that would be your median. All right? So measures of center versus skewness. Given our understanding now of why the mean gets biased by extreme values and the median does not, we can start to think about what happens with the relationship between the two depending on the skewness. So note here that on the symmetric distribution, mean and median are about the same. However, if you have a left skewed distribution, the mean would be pulled or biased towards the extreme values. So, in the left skewed distribution, you would have a mean that is smaller than the median because it's biased towards smaller values. In the right skewed distribution, you would have a mean that's biased towards large values because that's where the tail and extreme values are. So you would have a mean that's greater than the median. Let's apply this to our data set. Let me get out of the way here. Look at life expectancy in the 2000. If we do the spaghetti trick, we would see that there is a left skewed distribution here. So the mean would be pulled towards the smaller values. So here's the mean. Oops, I'm on the way still. So here is the mean, 67.12. Pause the video and think about it. Do you expect the median to be smaller or larger than that? You have to think about towards which direction the mean would be pulled to make that decision. If you thought the median was going to be higher, you're right, because the mean, as I said, is pulled towards the lower values where the tail, the extreme values are. Now, the difference is not huge, so this is not a horrible skew, but it is a skew nonetheless. Compare, for contrast, with life expectancy in the 1900. We talked about in the guided activity that the distribution in the 1900 is pretty centered. It's pretty symmetric, or at least more symmetric in comparison to this one. So we should expect mean and median to be closer together. Let's see if that's the case. Here's the mean, and here's the median. They're much closer together than this one. So that confirms that this is a less skewed distribution than this one. Testing your understanding of this. Days off at a mining plant. Workers at a particular mining site receive an average of 35 days paid vacation, which is lower than the national average. The manager of this plant is under pressure from a local union to increase the amount of paid time off. However, he does not want to give more days off to workers because that would be costly. Instead, he decides he should fire 10 employees in such a way as to raise the average number of days off that are reported by his employees. In order to achieve this goal, should he fire employees who have the most number of days off, least number of days off, or those who have about the average number of days off? Take a moment to think about it, pause the video, and then come back to hear the answer. So what does the sneaky manager wants to accomplish? He wants to create a scenario to display to the union that they are doing good with paid vacation. They want to raise the average up. So he needs to do what? He needs to leave in his workforce employers that have a higher number of days off, correct? Because that will pull the average up. So in order to achieve this goal, he should fire employees who have the least numbers of day off, right? Because then the distribution would be skewed towards employers with higher numbers of day off. Now, is this a smart move? Well, he's trying to be sneaky, but he ends up with employers in the end that have a lot more days off. He has been a biased, skewed distribution in a way that can impact his productivity in a way that he might not be expecting. Anyways, I digress. It's just important to understand that while that understanding how means are biased can help you think through your decisions based on data. All right. Hopefully not a sneaky way that makes workers' lives worse, but to make their lives better, you may need to use the same logic. Anyways, life expectancy around the globe. What is it? Has it changed over time? By how much? We have talked about so far in the class and also in the lab about the distribution, about the shape of the distribution, about a measure of center. But of course, we need to think about how precise our estimates are, and for that we need a measure of spread. How much confidence can I have in the measures of center that I got? How representative are they? And that depends on then the spread of the distribution around the mean. Here's an example of two distributions with the same exact center, one with a greater spread than the other. If I tell you that on the dark blue distribution, the average is, let's say, 70 years of life expectancy, is this a more or less precise estimate if our distribution looked like the dashed green distribution? If you said the center estimate would be more precise on the blue distribution, you're absolutely right, because the deviations around that are expected to be quite small. So you would have on average, 70 years of life expectation, and the variation would be not too much above that and not too much below that. Kind of an ideal scenario for the future of world health. But on the green one, it would suggest that we do have a pretty nice average of 70, but you do have a lot more countries that have lower and higher values than that. So greater disparities would be implicated by a distribution that looks like this one compared to this one. There are multiple measures, objective measures of spread. Range is one of them, which is easy. It's just the minimum score minus the maximum score. So you get like the absolute value of this difference gives you the full range of the data, right? The full maximum spread that you can see. But then you have others that are more nuanced, like variance, standard deviation, and interquartile range. We're going to discuss these three measures in the next video. I'll see you there. Bye.